it's Raychaudhuri, the Majorana-Raychaudhuri seminar series. Is that right pronunciation?
Yes.
Raychaudhuri, I see. Okay.
So we wait for another 1 minute and then we can start.
Okay, sounds good.
Actually, the first speaker finished early today, so that's why we have the.
Okay.
Usually we are always late, like talk starts 5 minutes, 10 minutes late.
I assume it's 45 minutes, including question times, right?
Yeah, but we are very informally, so if you want to be less or want to be more, it's fine. But
Okay.
yeah. But not for probably too long. Yeah.
Okay, thank you.
Yeah, so maybe we can start. So welcome everybody again for our second talk to today. Speaker is Kunio Kaneta from Niigata University, Japan, and he's going to talk about a closer look at gravitational particle production during the reheating era.
Okay, thank you. Thank you for inviting me and having me here this seminar series. So I will be speaking about the some aspect of gravitational particle production during reheating. This is based on the some series of works done with many people, but basically main part of my talk will be based on this first one, and some results given in the other papers are briefly just explained. So those who are interested in, please have a look at these papers at some point. Can I? What? Okay. So well, here's outline. Well, basically, this figure summarizes what I'm going to talk today. And I assume almost all of you are very familiar with inflation, but just in case that not familiar with the reheating, for instance, I'll just briefly explain the inflation and reheating just to set the stage of what I'm going to talk in the following, just briefly, and then move on to the main parts. The first one is about the perturbative aspect of gravity, the gravitational particle production, which is based on the Boltzmann's approach, and giving you one specific example. The simplest one is spin zero, and briefly explain the other cases like spin one and spin 3.5 if I have time. And then move on to the other aspect, which is non-perturbative, let's say. And this aspect can be explained in based on the volume approach. But in some cases, this aspect of this approach gives you the equivalent result to the Boltzmann's approach. And sometimes there's no such equivalence. That is what I'm going to talk. And during my talk, at any time, if you have a question, please stop me and ask a question. Please feel free. So let me begin with the introduction. Just let me make this very brief. So the inflation, the inflation universe can be easily modeled by introducing a scalar field called inflaton field. And the simplest one would be just drawing the potential look like this, and then put your inflaton at on top of the hill of the potential, and just start slow roll. Then what's important is that during that stage, the potential energy dominates over the kinetic energy. So that causes the exponential expansion of the space. That is the first stage. But then slowly moves down toward the potential minimum. And at some point, the kinetic energy of inflaton just dominates. I mean, it becomes comparable to the potential energy that's where the infraton starts oscillating about the minimum of the potential. That oscillation can be easily described by the equation motion for the homogeneous scalar field phi. And the solution is typically the damped oscillation. For this particular case, it's just a harmonic or damped harmonic oscillation. So the solution is very simple. And during this oscillation phase, the infraton just decays and transfer its energy to the other species, like the radiation. That's the so-called reheating phase. And well, in the following, I'm mainly focusing on this stage. Just once the inflation is over, it oscillates about minimum and then reheat the universe. Here's one specific example of the inflation, which is known as a T model, where the potential, the inflaton potential is given by a square of a hyperbolic tangent. The shape of the potential looks like a T, the letter T, so that's why it's called a T model. But why I choose this potential is just simple, because it's simply depending on a single free parameter lambda, which can be determined, well, fixed by the observation, the CMV observation. This potential, when the inflaton field value takes is much bigger than m Planck, the potential itself becomes constant, just constant. So it causes exponential expansion. But once the inflation is over, it starts oscillating about the potential minimum. And during that stage, the potential may be well approximated by the quadratic one, like this. And that's where the inflaton starts decaying to the other particles, like standard model particles. For instance, if inflaton has a coupling to the fermions, its decay width is given by here. Then the decay products of inflaton field forms the thermal bath. The energy densities of infraton and radiation can be easily can be easily seen by solving the set of Boltzmann equations given here. It's a couple of differential equations and easy to solve numerically. And what you find is that this kind of evolution of energy densities, rho phi and rho r, and well, once the inflation is over, the radiation energy densities are created, and at some point, it dominates over the energy density of infraton. And then at this crossover, we can define the reheating temperature by imposing both energy densities are equal, and the energy in such energy density, it can be parameterized by some temperature, which is defined as a reheating temperature. And typically, it is 10 to 14 GeV times some coupling constant here. That's basically it. But just for later convenience, let me explain a little bit more on the inflaton decay. So during infraton oscillation era, the infraton potential, as I said, infraton potential can be well approximated by the quadratic one. And during that phase, the equation motion of infraton can be given here, like this. And the solution, in this particular case, this differential equation can be analytically solved, but the solution can be decomposed into two pieces. One is the phi zero, which is corresponding to the slowly changing component. It's basically the redshift component. The other, well, is there anyone who has a question? No? Okay. The other piece is the periodic piece. The fast oscillating component which is in this case, it's just a sinusoidal function, and whose frequency is just given by the infraton mass. And the infraton energy density is given by the 0, 0 component of energy momentum tensor, averaged over some periods, which coincides with the just the infraton potential, but the argument is replaced by phi 0. For namely, it's given by like this. It's kind of averaged in energy density. The actual energy density is actually oscillating, but it's kind of, the energy density defined in this way, it's just red shifting. It's kind of corresponding to the envelope of the infraton oscillation. And the fast oscillating component, the periodic function P, can be Fourier expanded like this, and the Fourier coefficients are fixed by the solution itself. It's just given by some numbers, more complex numbers. Having said that, we can compute the decay rate for a given interaction of inflaton. For instance, for the decay of the nth mode of inflaton oscillation, the decay amplitude.
Actually, I also needed to ask something about my travel plans, but let's see
Sure.
once he comes back.
Oh, sorry. Is there any question?
No, I don't think so.
Okay. Okay, where was I? Yeah, here. So for the decay of nth mode can be, well, the amplitude can be simply computed based on the Feynman diagrams. But now the coefficient is just replaced by the envelope of the infraton oscillation and Fourier coefficient. Based on this amplitude, you can compute the energy transfer rate in this way, just summing over all modes, and then find result. You find this form, which turns out that it's the same as the normal, the regular decay rate of the particle at rest. This is actually not a completely coincidence, because now the infraton oscillation is just a homogeneous one. So the spatial component of momentum is just 0. So we can take the infraton oscillation as if it is just a particle at rest. So whose decay rate should be coincide. It should be the same as the decay rate.
Sorry, can I ask a question?
Sure. Yeah.
So I don't understand. So here you put the generic values of this Pn, or you kept the minimal case with just plus or minus 1?
This should be determined by the solution of equation of motion. And in this particular case, it is just the redshift component times just sine function. And for this is just only for this particular case, but just decompose the Fourier expand the sine, then you get this coefficients.
So, but in the computation of the rate later, you assume a generic function or this sine?
Yeah, well, this form doesn't depend on what coefficient the Fourier coefficient is. This form can apply any form of the oscillation.
So you get in any case the standard rate, even if this time dependence is non-standard?
No, yeah, right. Yeah, you're right. So if the potential looks like a different way, I mean, different form, then the P is not a simple sinusoidal function. But in that case, we can get the Fourier coefficients of this periodic function, and then you can use it to just plug it to the amplitude Pn.
Sorry, and the final energy transfer rate is this one or different?
Oh yeah. Well, well, it's a kind of detail, but if you choose a different form of the potential, you have to have a proper normalization, like depending on the equation state. But that's pretty much it. And the rest of the piece in this formula works as well in the same way. It is the same.
Okay, thank you.
Yeah. Okay, now I'm moving on to the main part, the portative aspect, one of the main parts, the portative aspect of the gravitational particle production. So first, let me briefly remind you about the graviton in a general relativity. For the gravity sector, we assume just the Einstein-Hilbert action, of course, with matter and gas fixing term. But in a normal way, as we usually do, we fluctuate the metric around the Minkowski background, and the fluctuation h mu nu is the graviton degree of freedom. And well, 2 is just a normalization to get the canonically normalized kinetic term. But anyway, the kinetic term for the h mu nu looks like this. And then it is straightforward to get the graviton propagator. It's just the bosonic one, but there's some additional polarization, the projection operator here. And then a graviton coupling to the other matter fields is given by the energy momentum tensor T mu nu here. So the gravity universally mediates between all matter fields in this way. Now, if you consider the dark matter, for instance, well, one may easily come up with the additional channel to produce, or universal channel to produce dark matter. In the energy momentum tensor, well, for instance, if we assume the minimally coupled dark matter, meaning we have a normal Einstein-Hilbert action, the standard model, and a dark matter sector, and there's no direct interaction between dark matter and standard model, or dark matter and the rich scalar, then still there's a interaction between the standard model and dark matter sector through the gravitational interaction. There, I think the first one to realize that the dark matter can be produced out of thermal bath by exchanging graviton. Well, what basically they consider is a scalar dark matter production from standard model thermal bath by exchanging graviton. The production rate of such dark matter pair is simply given by the temperature to the 8th over IM Planck to the 4th. That's a very easy calculation, on the dimensional ground, because amplitude is proportional to 1 over M Planck squared. So the reaction rate should be proportional to the M Planck to the 4th, or inversely proportional to the M Planck to the 4th. That gives you more or less good approximation for the number density of dark matter. Well, in the end, this is what they have got about the dark matter density. So for x-axis is the dark matter mass, and y-axis is a Hubble at the end during inflation. But well, detail doesn't matter. But the point is that just sufficient amount of dark matter can be produced by just gravitational interaction. That's what this is their conclusion. But almost at the same time, the other group in Japan noticed that this is not the main dominant channel to produce dark matter, but the dominant channel, dominant production channel is from the inflaton oscillation. That's actually sensible. right? Because at early time, the energy density of infraton is much greater than the energy density of radiation. And that is indeed the case. Here's a bit detailed, but the basic strategy is the same to how to compute the production rate. The same as the what I have explained in the previous slide about the decay rate. Just get the get the energy momentum tensor for infraton and Fourier expand, and then compute the scattering amplitude for the nth mode of infraton oscillation. That is well, this is the result. So the scattering rate, the production rate of a pair of dark matter from the nth mode of infraton oscillation should look like this. And then using this result, you can just go ahead and compute the production rate for the right-hand side of the Boltzmann equation. Well, this simple computation was first done by these people, Jan Breen and Keith Olive, for scalar dark matter. They also consider fermion dark matter as well, but let me just explain, illustrate the scalar dark matter here. The energy momentum tensor for scalar dark matter should look like this, and what they have done is just compute this Feynman diagram based on the graviton propagator and energy momentum tensors, then get the production rate, and then just solve the Boltzmann equation to find the dark matter relic abundance. Well, the conclusion remains the same as the case of the thermal production, but nevertheless, the sufficient amount of dark matter can be produced. That's their conclusion. Well, same exercise can be done for the other spins, like spin 1 particle. Here we consider the massive spin 1 particle. Now that there are two components, the longitudinal one and the transverse one, polarization, and for each polarization mode, we can find the radical abundance. We also have done for the other spin 3½ as well. Here we consider Raychaudhuri action, and then doing the same strategy, get the energy momentum tensor for spin 3½, and then just go ahead and compute the Feynman diagram to find the amplitude, and then get the radical abundance. But spin 3½ is a little bit subtle in the sense that there are some theoretical issues. One is a unitarity bound. For instance, if you consider the self-scattering process of spin 3½ and looking at the longitudinal mode, the scattering amplitude is proportional to the energy to the fourth. Well, the energy here typically is about the infraton mass scale. So we simply put the energy as an infraton mass to find this amplitude. And this should be greater than, well, it was smaller than 1, so that the unitarity is preserved. To satisfy that, we have to impose that the mass of spin 3½ should be greater than 40 EeV in this case. But well, this number is given by assuming there's no SUSY. So if there is SUSY, there are some additional channels like a torsion term for fermion operator for spin 3½, and by including that, this bound is somehow relaxed, like the lower bound on the mass of spin 3½ should be 0.1 EeV. But nevertheless, you cannot get a smaller mass to preserve the unitarity. The other issue is the known as a catastrophic production. So this is first pointed out by these people and later analyzed in detail by these people. The point is that if you look at the sound speed of a spin-3 Hawk particle, it should look like this. And during the infraton oscillation phase, the sound speed becomes 0 at some point, which leads to the constant distribution function. Constant means that the distribution function doesn't depend on the momentum. So the number density is given by, well, because number density is given by the integration of distribution function over momentum per phase space. Well, this integration gives you infinity in this case. So it's divergent. Well, one possibility would be if we include some back reaction process, like large number density. Well, huge production of spin-3 half has some back reaction to the background geometry. Such argument, the detailed analysis should be needed to narrow down this issue further. Okay. Now I'll be moving on to the next one. If you have question, please ask me. Now let me move on to the non-perturbative aspect of gravitational production. Taking the spin-0 particle production as an example, there's another way to compute the gravitational production. It's a bit complicated, but the idea is as follows. Since infraton is oscillating, there is a damped oscillation. Through the Einstein equation, the background metric is also oscillating, or haplo is also oscillating. This oscillation affect the time dependence in the kinetic energy of dark matter through this gravitational coupling. It's just a kinetic term, but there's a metric. So through this metric, this infraton oscillation affects the oscillation of kinetic energy of dark matter, and this time dependence in effective frequency leads to the particle production. Technically, this particle production can be computed based on the Bogoliubov approach or using the Bogoliubov transformation. What first people should do is look at the equation motion of produced particle and solve it by one numerical method, for instance. The equation motion, well, here we use this prime means that the derivative with respect to the conformal time. Anyway, it just solves the equation motion numerically, and then using that solution, you can compute the energy density. This is what they have done, and they indeed obtain the same conclusion that the sufficient amount of dark matter is produced in this way, the gravitationally. But now the question arises, so we have two different approaches to describe the gravitational particle production. One is based on the Bogoliubov transformation and solving the equation motion, and then find the energy density. The other is much simpler, based on the perturbative method, based on the Feynman diagram, and just compute the Feynman amplitude. Then solve the Boltzmann equation. That's much easier. Nevertheless, there are two different approaches to compute the gravitational production. Now the question is, are these two approaches equivalent or not? To answer or to address this question, here is one way. What I'm going to discuss discuss the distribution function computed in the Boltzmann equation, Boltzmann approach, and then compare it with the same quantity computed in the Bogoliubov approach, and to see if they are really equivalent or not. In doing so, the question maybe is stated in a different way. Basically, the Boltzmann approach is based on the QFT in Minkowski space-time. So the particle production is described by the collision terms in the Boltzmann equation. On the other hand, the Bogoliubov approach is based on the QFT in curved space-time. And particle production is described by the time dependence in effective frequencies. They look very different approach. So there are no guarantee that they are equivalent. Okay. So first, let me explain the first one, the distribution function in Boltzmann approach. This is basically the same argument. We are looking at this diagram. Initially, the oscillating infraton annihilate into a pair of some spin zero particle here, for example. And Lagrangian is the same still. But now since we want to know the distribution function of produced particle, we are solving the Boltzmann equation for the distribution function f chi. It's a kind of straightforward computation to get the equation term in the right-hand side of the Boltzmann equation, and you find this form of the equation term. Normally this type of Boltzmann equation cannot be solved analytically, but fortunately, this particular case, it can be solved, and then the solution is given like this. Now, K is a comoving momentum. It's rescaled one, rescaled physical momentum. And detail is not important here, but the point is that the distribution function is proportional to the momentum to the minus 9/2. That is the result of the Boltzmann equation. Okay. Now let me move on to the other approach, the Bogoliubov approach. But let me here briefly remind you the QFT in curved space-time, just one slide. In the following argument, I'll be using the conformal time instead of just comoving time. And we will rescale the original chi field multiplied by A inverse, so that the action look like just a free field theory. But now the frequency, the effective frequency omega depends on time through scale factor A or R. Now, because frequency omega is time dependent, so the wave function, for instance, in the past, is different from the wave function found in the future, which means that if we define the vacuum in the past by using the wave function in the past, then that vacuum is not the same as the vacuum in the future. This relation can be explicitly written down by introducing the Bogoliubov coefficient, alpha and beta. Here, the A and A dagger are the annihilation and production creation operators in the past, and this is related to the annihilation and creation operators in the future through the Bogoliubov coefficients. And if we define the vacuum in the past by using the A, then we ask how many particle is there in this vacuum in future. That can be obtained by applying the number operator defined in the future on to the vacuum in the past, which is beta square, and this is generically non-zero. So there's a particle production. Now we want to find this beta to find, that is nothing but the occupation number, or in other words, it is the distribution function. That's what we want. So then volume of coefficients alpha and beta, it is relatively straightforward to find that the alpha and beta follow this type of differential equations. Then, well, of course, you can solve this coupled differential equation numerically, but in some cases, we can approximately solve this differential equation for beta. So that is when the omega prime is much smaller than the omega square. So the second term here is much smaller than the first term. In this case, the second term can be treated as a perturbation to the first one. So the solution for beta can be obtained by integrating over this factor. And in a particular case, we know the form of this integrand, and making further approximation, because we know the specific solution, a concrete solution for inflaton oscillation here, and we know how the Hubble evolves. This is just the evolution of the the redshift contribution, and then making an appropriate approximation, like looking at the very large momentum compared to the background, the curvature, and expand in terms of the Hubble over inflaton mass, then you find this expression. And this is just a leading order contribution, and one is coming from the fast oscillating contribution from inflaton, which should be multiplied by the fast oscillating component coming from the decay the produced particles. So normally, the integration over the oscillating integrand gives you 0, because random phase cancels with each other and leaving 0. But in some cases, when these two fast oscillating pieces are canceled, then you get the finite result for the after integration. That's what you find for the this beta coefficient. It's nothing but a stationary phase approximation, and you find beta square in this form. It's going like k to minus 9/2, which is, if you remember, exactly the same as what you found in Boltzmann approach. So it turns out these two approaches are equivalent in this case, namely for a large momentum case. But this is not the end of the story. There's another channel to produce particle. That's coming from the sudden change in the background geometry from the zeta, the inflation, to a matter domination, the inflaton oscillating phase. So the effective frequency of chi during inflation is not the same as that in the matter domination era, which indicates that there's a particle production. The taking Bunch-Davis vacuum as an initial condition, you can find the how many particles can be produced from this, the change in background geometry. This is two cases. Well, depending on the mass scale of the produced particle. Let me explain a little bit more in the next slide. Here's a schematic picture of the particle production in this case. There's a sudden change in the background geometry. Well, basically, you can solve the equation motion in either the zeta or matter domination, and these two solutions are not the same, but they have to be smoothly connected at the end of inflation. So by using the matching condition, you find the alpha and beta, the value of coefficients. This is the basic strategy. And what's actually happening in this case is that is shown in this figure. The x-axis is a conformal time, and y-axis is a comoving momentum k. And this line indicates that the effective frequency becomes 0. This as well. Above this line, the omega square is positive, and below this line, omega square is negative, meaning it's tachyonic solution. And we start at outside the tachyonic region, somewhere here for higher momentum, and imposing the Bunch-Davis vacuum. So there's no particle initially, and as time goes, and then the wave function enters the tachyonic regime and then gets enhanced. And then after the end of inflation, again, it comes back to the non-tachyonic regime, and then you find there's a particle production. If the momentum bigger than Hubble, well, HE is the Hubble at the end of inflation. If the K is bigger than this scale, the wave function stays just a plane wave, so there's no particle production. It's identical to the vacuum. And depending on when the wave function comes back to the non-tachyonic regime, the shape of the distribution function changes. So this point is determined by the mass scale of the produced particle. So if the momentum is bigger than this scale, the distribution function goes like k to the -6. And if k, the momentum is smaller than some typical mass scale, the distribution function goes like k to -3. So it's sort of non-relativistic case. Now we have seen that there are two regimes about the particle production, or gravitational particle production, depending on the momentum of produced particle. One is when k, the momentum is bigger than Hubble or inflaton mass. In such a case, the particle production can be regarded as the scattering process of inflaton to produce a pair of particles, spin 0 in this case. And in this regime, both Boltzmann approach and Bogoliubov approach gives you the same answer. So in this case, maybe the Boltzmann is the way you go for. It's much easier to compute. On the other hand, if the momentum is smaller than the Hubble scale during inflation, the Boltzmann approach doesn't work. and only the Bogoliubov approach can deal with. There are two distinctive regimes in the phase space, the whole range of phase space. The one is the hard spectrum. As I said in the previous slide, that it's produced by energetic scattering process. And for the soft spectrum, there are two regimes. One is the soft relativistic regime, which is when the momentum k is bigger than some mass scale. And if momentum goes below some mass scale, typical mass scale, then it goes like a k to minus 3, which is soft non-relativistic spectrum. Okay, so let me summarize. As I explained earlier, there are two regimes in the gravitational particle production. And if the particle momentum is much greater than the infraton mass scale, both approaches gives you the same answer. If the momentum is much smaller than the infraton mass scale, then you have to use the Bogoliubov approach. And there are main characteristics about the spectrum. For the hard spectrum, well, it is anyway unavoidable, and as long as we have infraton oscillation, and well, it depends on the spin and the weight of infraton oscillation. In this talk, I just focus on the quadratic oscillation, harmonic oscillation, but it can be easily extended to the other type of oscillations. And for the soft spectrum, in many cases, this contribution cannot be negligible, but it depends on spin and also interaction of the produced particles. For instance, if chi field has self-interaction or interaction with other particles, then the spectrum should be changed. So it strongly depends on the model.